Here's our first example. Find all solutions to cosine x equals 0.28. We hopefully have some quantities around the unit circle memorized, values for cosine like 1/2 or radical 2 over 2 or radical 3 over 2 or 0 or 1 or -1. But 28/100ths is not a value that has popped up before, especially among our main increments on the unit circle. So we'll need to use an inverse trig function. We're after what angle is it that gives us a cosine value of 0.28, so that angle is found by doing an inverse cosine of that value, 0.28. This equation is how we can find what angle is it that has a horizontal component of 0.28. And I'm thinking horizontal because we're looking at a cosine function. Punching this into the calculator, in degrees I get approximately 73.74 degrees, and in radians, approximately 1.287 radians. That location would be around right here on the circle. This should make sense because our original equation was searching for what angle has a cosine of 0.28, a horizontal component of 0.28 units, and we can see after moving horizontally 0.28, a vertical move would get us to that point at about 73 degrees. We could find that vertical component using a Pythagorean theorem, figuring out what the sine value is, but if that sine value is positive, it corresponds to this point right here, about 73 degrees. But there is another point on the unit circle that also uses a horizontal component of 0.28, but can be found with a negative vertical component, with a negative sine value. So we will need to find this other value. The calculator will only find one inverse trig value for us because those inverse trig functions have a range that is only half of the circle. Inverse cosine will only find the result that is on the top half of the circle. We will need to then determine where the other spot on the circle is on the other half of the circle. In this case, with a positive cosine value, we could have a corresponding positive sine, which would put us in quadrant 1, or we could have a corresponding negative sine value, which would put us down in quadrant 4. How do we determine exactly what this other degree measure is? Well, the one that we got from the calculator, 73.74 degrees, is a rotation from the origin in this counterclockwise direction, the positive direction. Our other point down here would be a result of the same amount of rotation but in the opposite direction, so about negative 73 degrees. And our initial position is 0 degrees or 360, so we can subtract 73 degrees from 360. We're basically saying in the positive direction we start at 0 and rotate 73 degrees to get here. And our other point, if we begin at 360 and backtrack by 73 degrees, we'll end up right here at about 287 degrees. So when I subtract from 360 my original value, 73.74 degrees, I get my other value, the other answer of what angle gives us a cosine value of 0.28. The other one is 286.26 degrees, and that is this point down here in quadrant 4. What should I do if I'm working in radians? The locations are still the same. The only difference is I'm not thinking of my full rotation as 360 degrees, but how many radians? 2 pi radians. So from the 1.287 radians I found from the calculator, I'll think of that being a negative rotation backtracking from 2 pi, and this subtraction leaves us with approximately 4.996 radians. So working in degrees, we should get 2 answers. If we're working in radians, we should get the same thing as in degrees, 2 answers. And the calculator will only give us 1 because the range of inverse trig functions only spans 1/2 of the circle. So the calculator will only determine one of our answers. We will determine where the other one is based on reflections and positive and negative angle measures. One more thing to point out would be this question asks for all the solutions. So that is actually asking us to have an answer that represents the fact that I could make several rotations around the circle and then land here. So by that I mean I could say 360 degrees plus another 73, that's 433 degrees, would put me at this same spot. So if I want to represent all the solutions, Well, let's start with degrees. These were the two that we came up with. Now I want to represent, I could include any extra number of rotations, any extra number of 360-degree increments. How can I represent this statement that can be 1 more, 2 more, 3 more rotations, and so on? We'll take the 360 and multiply it by some number k, and say that k has to be an integer, 0, 1, 2, and so on. If k equals 0, then this term is wiped out completely, and we have our answer that is in between 0 and 360, both of them. If k equals 1, now we're talking about 1 additional rotation. If k equals 2, 2 additional rotations, and so on. So we include this plus 360k term to represent additional rotations, and then we say that k has to equal an integer. You could state it this way by starting a list, or you could write k is an integer, or you could use this symbolism. K is an element of, this is just a fancy z, which is used to represent the set of integers. How would it look in radians? Again, we'll start with those two solutions in radians, but this time extra rotations won't be adding in 360 degrees, it will be adding in 2 pi radians. We'll still multiply that by k so we can scale how many extra rotations we want, and state that k has to be an integer. This is the only time in this video where we'll represent our total solutions, so be cautious about the questions that you're handling. What are they actually asking for? If we want all solutions, then I want to see answers like this, where we're accounting for possible extra rotations. But usually we get these questions that say, find all solutions between 0 and 360 degrees, and then we'd know to find answers in degree measure. Or it would say find all solutions between 0 and 2 pi, and then we would know to work in radians. Let's go through several more examples. We want to hit sine and tangent, and then explore some other different equations that we'll encounter. Next, sine of x equals negative 0.55. Again, not a value that we're used to seeing from our main points on the unit circle, so we need to use an inverse trig function. X will equal inverse sine of negative 0.55. Punch that in, and now we come up with negative 33.37 degrees, which is down here in quadrant 4. Now, it's giving us a negative value again because of how the inverse trig functions work. An inverse sine function gives us values only on the right half of the circle, and the range is thought to be in between negative 90 degrees and positive 90 degrees. So points in quadrant 4 are going to come at us if we use an inverse sine function as negative values, whether it's degrees or radians. So let's quickly take care of this negative angle measure. We make it positive by adding 1 complete rotation to it. Add 360 degrees. It will keep us on that exact same point, but now we have a positive angle measure, 326.63, which we definitely recognize as a value here in quadrant 4. This angle measure should make sense to us if we think about the original equation. Sine of x equals negative 0.55. This equation is stating that there is an angle where our vertical component is negative 0.55, and I'm thinking vertical because now it's a sine function. So from the origin, moving vertically by negative 0.55, I can see I would arrive at our location with a positive horizontal or a positive cosine value. But we can find another point on the circle using the same vertical component of negative 0.55, but if we used a negative horizontal component, we have a point right there. Now we saw with cosine that our points were reflections about the x-axis. When it's sine, our points are reflections about the y-axis. If we know that this point was found by going from original position and coming back by 33 degrees, remember our original calculated value was negative 33.37 degrees, it's also going to be about 33 degrees from this point here down to our location here in quadrant 3, based on symmetry of these points. So 33 degrees clockwise from original position to this point here in quadrant 4 matches up with 33 degrees from this point in a counterclockwise direction to our location in quadrant 3. How can we determine exactly the degree measure here? Well, at this point, we've already traveled 180 degrees, so we'll add to the 180 degrees the 33 more degrees, and this value, 213.37 degrees. So that's how we're locating our second angle measure that gives us a sine value of negative 0.55. If we're working the problem in radians, then our original calculation inverse sine of negative 0.55 will give us a negative radian measure, just like we got a negative degree measure. Let's quickly take care of that and say we can add a complete rotation to get us from negative into the positive. Add 2 pi, because we're in radians, we get to about 5.701 radians. That is our location here in quadrant 4. How do we determine the location here in quadrant 3? Same way, except instead of this point here being 180 degrees, what is the measure here in radians? Pi radians. Pi plus another 0.582 radians will take us to this location in quadrant 3, about 3.724 radians. So we've covered a cosine example and a sine example. Now let's do tangent. Tangent of x equals 1.25. Again, not a value that we're used to seeing from main points on the unit circle, so I'm using an inverse tangent function. Inverse tangent of 1.25 equals x. Now, when we were talking about cosine, we were thinking about a horizontal component and sine as the vertical component. When we're looking at tangent equations, we should be thinking about slope. Tangent x equals 1.25 is an equation stating that we have an angle that has a slope of 1.25. Slope because it is a tangent. But like the other inverse trig functions, we only get values from the calculator on a half of the circle. When I punch in inverse tangent of 1.25, in degrees 51.34. That's corresponding to a point here in quadrant 1, and when we think about slope, we're thinking about the slope of a line from that point through the origin. I would know that the slope of that line going through quadrant 1 should be positive, so I'm doing all right that it started out as tangent x equals a positive 1.25. Where do we go to find the other point on the unit circle that has the same slope? It won't be about reflections because we're not interested in x values, that would be for cosine. We're not interested in the y values, that would be for sine. Tangent is for slope. And where we'll find the point that has the same slope is going to be a point on that same line. Through this point here at about 51 degrees, a line going from that point through the origin all the way to the other side of the circle in quadrant 3. That is our second angle solution to tangent x equals 1.25. With tangent, it's always easier to find this corresponding measure because it's always 180 degrees on the other side of the circle. So our first solution, 51.34 degrees, I'll add 180 to get the second solution, 231.34 degrees. If we're working in radians, punching in gets our answer 0.896 radians, again corresponding to the same location in quadrant 1. Our other point, still on the opposite side of the circle, but since we are in radians, we won't use 180, we will use pi. Adding pi to our original solution gives our second solution 4.038 radians approximately. I do want to point out that if we don't see units, we assume radians. Degrees, we definitely want to include the degree symbol, but radians, we often let that unit go. And if we don't see units, we should be assuming radians. Don't assume degrees. I do want to talk about, with tangent equations, how do we represent all the solutions, because we can do it in a little bit more of an efficient way than how we did it with cosine or how we would do it with sine, which it would be the same way between those two. Think about why this would be sufficient for representing all the solutions in degrees for this equation. I don't have both of my values listed and adding on full rotations of 360 degrees. I only used one solution, and I'm adding in additional rotations, only half rotations, 180 degrees. That's all because of, with tangent functions, we find solutions 180 degrees on complete opposite sides of the circle. So when I pick out just my first one, at 51.34 degrees. Adding 180 will take me to my second one. Adding 180 again is now the effect of a full rotation and back to my original point. So tangent, I only have to pick one value and say you can add to it 180 degrees as many times as you want. 180k, where k is an integer. And if we're talking about radians, halfway around the circle would be only pi radians. 0.896 plus pi k, where k is an integer. With sines and cosines, we don't, as a rule, have an efficient way to write it like this. We'll have to do it the way we were doing it earlier, where we list both of our answers, and if they're degrees, we say either one could add 360 degrees to it, or if we're working in radians, either one of those solutions we could add 2 pi radians to it. Only with tangent, we're able to say just pick one of those solutions, and you could add 180 degrees or pi radians to it. Let's take these equations up one notch with this example. 3.5 times cosine x minus 1 equals 0.75. Well, what we need to do to solve for x first would be isolate the function cosine x. Using our properties of equality that we use for solving all other types of equations, I'll add 1 to both sides and then divide by 3.5 to isolate the cosine of x. Cosine x equals 0.5. Now this is a value that we do recognize from main measurements on the unit circle. So we're going to go back to some memorized values that we have. Cosine x is 1/2. So horizontally we're talking about moving positive direction 0.5. We have a corresponding value vertically positive, and another one if we were to go downward in the negative direction. And those again are main points on the unit circle. They're at 60 degrees or 300 degrees. In radians, pi over 3 and 5 pi over 3. Now you ought to have those unit circle values memorized. If you don't, you can still accomplish this problem as we did those previous examples where we were punching in the inverse trig functions into a calculator. But I think you'll be better off in the long run by having these unit circle measurements memorized. So when I see cosine x equals 1/2, I immediately recognize points on the unit circle that have an x value of 1/2. And these are the points that are 1/2 with radical 3 over 2, and down here would be 1/2 with negative radical 3 over 2. And because it's cosine, we see that our two solutions are reflections about the x-axis. When we deal with sine functions, they are reflections about the y-axis, and in tangent, they are 180 degrees away from each other. I'll continue to show solutions in degrees and radian measure both, but usually along with our question we get some instruction about what sort of answers to give. We would give degree solutions if we saw something with our question that said find solutions in this range between 0 degrees and 360, and a square bracket on 0 to say that if we want to represent the angle measure right at 0, choose 0 but avoid using 360 degrees. And if we're in radian measures, we'll see find solutions in this range, 0 to 2 pi, and if we're right at our initial position, choose to use 0 radians instead of 2 pi radians. So around parentheses on the higher values of the range. Let's take things up one more notch. 2 times sine squared x equals 1. Again, we should isolate our trig function, divide both sides by 2, we get sine squared equals 1/2. Now before we go over to the circle and picture where these solutions should be, we do want to take it down from a sine squared to a first degree sine. This is an equation where we would want to cancel this exponent of 2 by doing a square root both sides. Just like if this equation was x squared equals 9, we would square root both sides and get x equals... Now, do you remember what we would do with square root equations? We have to be certain that we account for a positive or a negative answer. If it was x squared equals 9, our solutions would be a positive or negative 3. So that business is still going on here. We choose square roots because we have a sine squared. That does simplify it to sine x, but we have a positive or negative right side, square root of 1/2. Hopefully we recognize square root of 1/2, And if we rationalize the denominator, definitely we'll see something familiar, radical 2 over 2. So we'll be able to use some unit circle information, but the way that we have to proceed from here is to understand that we now have two separate equations to work with. We have sine x equals a positive radical 2 over 2, and we have sine x equals negative radical 2 over 2. So let's handle these one at a time. First, sine x equals a positive radical 2 over 2. Hopefully we recognize a radical 2 over 2 would be at the measures 45 degrees, 135, 225, or 315. A positive sine, so a positive y value, positive vertical component, would pick out these 2 points. With sine x equals negative radical 2 over 2, that's going to be our 2 negative y values. So those measurements are at 45 degrees, 135 degrees, 225 degrees, and 315 degrees. And in radians, pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Now let's do one where we do square roots with a tangent function for fun. Again, we'll have to isolate the tangent. I'm subtracting 1.1 from each side, and then divide by 1.4, down to tangent squared x equals 1.5. Again, it will be square root to both sides. Takes us to tangent x equals positive or negative square root of 1.5, approximately 1.225. Now I want to tell you I'm not rounding here. I'm keeping this entire value of square root of 1.5 in the calculator, that when I go and do inverse tangent, I'll be able to use that entire number. As always, I would avoid rounding until the very end of the problem. So I've chopped it off here, but understand that when I do my next calculations, I'm still using the entire value in my calculator, square root of 1.5. Now to proceed from here, I'll need to use an inverse tangent function. X equals inverse tangent of positive 1.225, and our second equation produces x is approximately, and I have to include approximately because I did round my 1.225, inverse tangent of negative 1.225. Punching in over here gives a result approximately 0.886 radians, or 50.77 degrees approximately. Now that is our first solution because inverse tangent only gives us values on the right half of the circle. We need to locate the other value on the left half of the circle. Here's the location the calculator found. Our other location will be exactly 180 degrees on this same line that cuts right through the origin. So to the degree measure I'm adding 180 degrees. To the radian measure I added pi radians. Now moving over to the other equation, inverse tangent of negative 1.225. We're looking for angle where our slope will be negative. So hopefully we're getting a result in quadrant 4 or quadrant 2. And if we know inverse tangent uses the right half of the circle, we should expect answers in quadrant 4. And even more, we should expect negative results because the range of inverse tangent is negative 90 degrees to positive 90, or negative pi over 2 radians to positive pi over 2 radians. So here we see those negative values. We should pretty quickly change those into positives. Do that by adding a complete rotation. Add 360 degrees to negative 50.77, and add 2 pi radians to the negative 0.886. Takes us to these values here, confirming, again, we have them here in quadrant 4. Now where do we find the matching value? Here we are at 309.23 degrees, or 5.397 radians. We're going 180 degrees away, opposite side of the circle on this straight line, to find our other point. Now before we were adding 180 degrees, but I won't do that this time because it's going to pop us over 360. I'll do instead subtract 180. So I'm still going to opposite side, a difference of 180, but I would like to stay in that range of 0 to 360 degrees, or 0 to 2 pi radians. So subtracting 180 degrees leads us to 129.23 degrees. Subtracting pi radians, only pi because we want to go halfway around the circle, 2.255 radians. Taking things up one more notch, with this example, cosine squared x minus cosine x equals 2. We want to observe we've got cosines here, but one has been squared, and we have one that is degree 1. We should work this equation like it is quadratic. I'm getting all of my terms on the left side equal 0, and now looking at it, perhaps we could factor, and we can. We're handling the cosine x function like it itself is the variable. So here's our variable squared, our variable to the first degree in the middle term, and we're ending with a constant. I'm still looking for a pair of numbers that multiplied would equal negative 2, added up would equal negative 1, our coefficient of the middle term. So I have it factored this way. We know solving by factoring each of these factors equals 0 leads us to cosine x equals positive 2, and this side, cosine x equals negative 1. The cosine x equals 2, we can toss that out right away, because cosines and sines only give us values between negative 1 and positive 1. So when we see an equation like this, a cosine equals 2, there is no angle that gives us a cosine value of 2. The other equation, we can do something with this. Negative 1, that's a point we should know about our unit circle. Where do we have a horizontal component of negative 1? Horizontal because it's cosine, and here is that point, horizontally negative 1. Our angle there is 180 degrees, or pi radians. This equation has only one solution. If we get to solutions that are on an x-axis or y-axis, be cautious about our reflections. Cosine, we know that our solutions are reflections about the x-axis, but if our point is right on the x-axis, it doesn't have a distinct reflection. But if this was a sine equation, I would be able to find a reflection about the y-axis. So always remember what we know so far about reflections, and the unit circle will be just fine. We're starting to get everything, all of our important ideas, all together into a nice flow through these problems. Next, hopefully you're recognizing we have another quadratic. We've got sine squared x, and we have a regular sine x. Let's get this into a standard form with all the terms on one side of the equation equal to 0, and now try to factor. I've got a leading coefficient of 2, so it's taking me a little more time here, but I like this strategy. If I don't feel like writing sine x over and over again, let me just, for the moment, replace that sine x function just with an s. I have what's a more familiar looking polynomial to work with. I'll be sure to put a sine x back in after I do all my steps, but as I figure out how to handle this quadratic, I'm just going to use s instead. So I see I can do a factor by grouping if I split this middle negative s into a negative 2s plus s. Here's a factor by grouping. S minus 1 times 2s plus 1. I could even go ahead and solve. S equals 1. S equals negative 1/2. And now let's bring back in that our s really was in place of sine x. So here are the two equations we need to wrap up to solve this equation. Sine x equals 1. Hopefully we know this on the unit circle. Where's our angle that has a vertical component of positive 1? Right up here at 90 degrees, or pi over 2 radians. And now over to sine x equals negative 1/2. Again, those are big ones on the unit circle. We have them here. Now vertically negative, so hopefully I've narrowed it down to quadrants 3 and 4, and if I have my unit circle memorized very well, I would say right away, happening at 210 degrees and 330 degrees, or in radians, 7 pi over 6 and 11 pi over 6. And just one more reminder, if you just have chosen not to memorize the unit circle, you can still accomplish these problems punching in and doing an inverse sign on the calculator. But deep down, I'm hopeful that you don't do it that way, that you've got these points, these values memorized. Let's do one more quadratic. 10 cosine squared x plus 5 cosine x equals 2.4. Again, visually, I'm recognizing a quadratic. I'm getting everything onto the left side. I'll go ahead and put c's in place of the cosine x while I work with this quadratic. Turns out we could factor this, but I want to use quadratic formula just to tell you that, we're looking at a quadratic, we're trying to solve. When we do solve it, we'll get cosine x equals, not just what x equals, so there will be more steps to do, but however I choose to solve the quadratic is going to be valid. I could complete the square, I could use quadratic formula, so I'm going to use quadratic formula here. A is 10, B is 5, C negative 2.4. Here's plugging into negative b plus or minus square root of b squared minus 4 times a times c gives me this negative 96, all over 2a, 2 times 10 is 20. Here's where we see some things that could be simplified. 25 minus negative 96 is actually 121. Square root of 121 down to 11. Let's finish solving by breaking this up into two separate fractions. We'll have cosine x equals a negative 4/5. If we did negative 5 minus 11, we'll get a negative 16 over 20, simplified to negative 4/5. If we go with the plus negative 5 plus 11, we end up with 6 over 20, or 3/10. Now I'll go and use an inverse cosine function on the calculator. Inverse cosine of negative 4/5 first. Now let's get an idea of where these points are. Cosine x equals negative 4/5. So we're talking about an angle that has a horizontal component that is negative 4/5. From the origin, I'm seeing moving horizontally out negative 4/5. And I see two corresponding points. One we could get to with a positive vertical, and one we could get to with a negative vertical. Punching in, I get approximately 143.13 degrees. That degree measure is our point here in quadrant 2, a positive rotation of 143 degrees. We'll get to our point here in quadrant 3 by thinking of a negative rotation. It's a reflected point about the x-axis. So from initial position, let's back it up by 143.13 degrees. So I'm doing 360 minus 143.13 to get this value 216.87 degrees. If I'm in radians, punching in, I get 2.498 radians. Same idea, except instead of backing from 360 degrees, I'm backing up from 2 pi radians. 2 pi minus 2.498 equals 3.785. So there are the 2 points from this equation where cosine x equals negative 4/5. We still have to follow up with this equation here. Let's get an idea of where these solutions would be. A horizontal component of 3/10, positive 3/10, going to the right of the origin. And we will have corresponding points going positive vertically and going negative vertically. There are the two reflections on the x-axis. Punching into the calculator, I get 72.54 degrees, or 1.266 radians. That's our location here in quadrant 1. To find location in quadrant 4, same moves basically. Here's a positive 72.54 degrees. So the other way, let's start at 360 and backtrack by 72.54 degrees. Or in radians, begin with 2 pi and backtrack by 1.266 radians. And that will lead us to our last two results. In degrees, 287.46, and radians, 5.017. So here's an equation that had 4 total solutions. Here are the 4 in degrees, here are the 4 in radians.